online on YouTube?
Yes.
Okay, now we are on only streaming on YouTube. So then I will start a brief introduction. So Professor Archang Li received his PhD from National University of Singapore in 2011, and then worked as a postdoc and later research scientist at King Abdullah University of Science and Technology in Saudi Arabia. So in 2016, he joined the Department of Modern Mechanics at the University of Science and Technology of China as a professor of fluid mechanics. So his main research interest is on drop dynamics and has published more than 60 journal papers. So today we are very happy to have Professor Archang Li to introduce his work on the mass transport in drop dynamics. Archang, it's your time.
Okay, thanks, Prof. Jane, for the very nice introduction. So good morning, good afternoon, good evening, everyone. So I'm very happy to have this opportunity to participate in this nice seminar series. Today, I would like to share with you our recent work on mass transport in drop dynamics. Basically, I will focus two main parts. Okay, the first is the Lamella evolution in drop impact problems. The second is the force or the inverse square force we discovered for the droplet systems, especially between two evaporating session droplets. Okay, so first I would like to give a short background on why we should care about drop research. Because now I think almost everyone aware of that. It is very important to wear masks because the coronavirus. So because one of the mechanisms of the transmission of the coronavirus, as well as many other infective diseases such as SARS, MERS, and rubella, one transmission method is through the droplets or aerosols produced by talking, speaking, sneezing, coughing, and etc. So the virus can be transferred from the patient to the healthy people. So it's important for us to understand how droplets is travel in the air. This video comes from Professor Lydia. So from this video, we can see how we produce this kind of droplets or aerosol when we're talking or coughing. Yes, you can see it's a very nice video. Okay, this video shows the trajectories of these small droplets travel in the air. And if we sneezing, the drop can fly 8 meters. I mean, if there's no wind, and if we cough, it can fly 6 meters. So to understand how these droplets will move in the air is highly useful for the prevention and control of the infectious diseases, and especially if we design the buildings such as hospitals, schools, etc., to design the ventilation system. Okay. Another example is in the advanced technology, especially we know asthma company in the Netherlands is very famous for its extreme ultraviolet lithography system. So one of the secrets of asthma's success is to use the so-called immersion lithography technique that is proposed by Mr. Benjamin Lin. So the idea is to use this liquid meniscus instead of air before it's air. So replace the air. What is the advantage is it can change the wavelength of the light from 193 to 157. So greatly enhance the resolution of the technique. But one very challenging problem is these meniscus have to move together with the lens at a velocity, let's say about 0.7 meters per second, it's a very high velocity. And during the process, it should not leak. So actually it is a fluid mechanics problem. Also, we call it moving contact line problem. Also, in this technique, the ultraviolet lithography, I mean the light, is produced by heating the thin droplets by powerful lasers. So the the breakup of the thin droplets and also the plasmonation process is also a drop dynamics problem. So from these two examples, I hope we realize that drop research is important to our daily life and high technologies. Accordingly, droplet research has gained more attention in the research field. In this table, I organize or summarize the number of articles published with title contain either drop or droplets in JFM and PRL. So for the past 5 years, you can see the number of publications is like 239 and 114. If we compare even earlier, the 5 years, 2012 to 2016, the number is 141 and 75. So the increase is like 69% and 52% respectively. So we can see job research has become more and more hot topic. Okay. So if we want to do job research, what we should do or what we can do, this table may be not correct. I just classify it into different types. From the perspective of process, I would like to see job research can include job generation, either by gravity, like raindrop, or by microfluidics technology, or job coalescence, breakup, impact, and phase change. For example, like evaporation. I think you have enjoyed the very nice talk by Dr. Yaxing Li 2 weeks ago. He have talked about this topic. And I think this two elegant paper is from him. And from the perspective of purpose, I would like to see we either focus on mass transfer in drop dynamics, either heat transfer or energy transfer. That is what we concern always, right? Like mass and energy. Okay, so go to my second part. The first example I give is the laminar evolution in the early stage during drop impact. Okay, drop impact is not a new problem. Centuries ago, sailors have realized like the rain can help to calm surface waves on the sea. This has roused the interest of Reno, who has studied the drop impact problems and led him to find or discover the vortex rain produced by drop impact problem. Then later, Arthur Watson, we have, I think if you do drop impact or related topics, you have be familiar with this number names. And also Sir Joseph Thomson, he won the Nobel Prize in Physics for discovering electrons. But in the early stage, he also drop impact experiment. They did some very nice work in these topics. Okay, nowadays, another topic is to investigate how can we produce a cavity during water entry problem. You may ask, you are talking about drop impact, but why you now link to water entry problem? I will later show that to me, these two problems are the same, especially if we investigate the early laminar evolution. So why we care about cavity formation? This annual review paper from Professor Truscott is a very good example. I mean, so basically we are interested in this phenomenon, not only because of the beauty, because it also can benefit to our applications. For example, if you have a sphere, you throw it into liquid, it will sink if the density is larger than liquid, right? If it is look like this shape, it will produce a wake behind it, which will inert some drag on it. And if it can produce a cavity like this, you have a streamline configuration shape, then the drag will be reduced. So this is useful for many applications, for real applications. So how to promote cavity formation? There are basically two types methods in the literature. One is from this very nice paper from Booth and colleagues. They realize if you increase contact angle of water on the solid surface, or we see if you change the surface variability of the surface, you can change how the cavity is formed. Especially, let's see here, if your contact angle is larger, then the threshold velocity or the minimum velocity you need to produce a cavity reduced. That means for a high contact angle, it is easier to produce a cavity. My previous group, like Professor Sorensen's group, in Saudi Arabia. He and his colleague, Dr. Vaklaski, they use another effect, the liquid-infused effect, to produce this nice cavity. They also can realize drag reduction. Okay, so now I would like to ask, because a sphere with a free slip surface represents the theoretical limit at which resistance to motion can be minimized. So how, if we use a slippery liquid-liquid interface, what it will bring to the formation of the cavity, whether it will be a more effective method. So that is the focus of my first talk. So we refer to the, sorry, something happened here. So we refer to the slips method or technique. Basically, it is inspired from this plant. What you do is you produce a structure solid surface with macro or nano structures or holes inside it. Then you put a lubricating film. Usually is an inert oil with low surface tension. You put this oil on it. Then if you have another liquid which is immiscible with this lubricating film, you put the droplet on it, you will get extremely low contact angle hysteresis. And it can be used for many applications such as drag reduction, self-cleaning, this kind of thing. So what we do is we use laser to scan on a metal sphere and to produce these textured surfaces. Then we put the lubricating film onto it. To compare, because from those paper, we know that contact angle is very important for cavity generation. So to remove the effect from contact angle, we make sure we choose a slips oil or the lubricating oil to make sure the water contact angle on this oil is the same as this hydrophobic sphere. So they are 110 degrees. So we don't have extra effect from contact angle. Then we throw a hydrophobic sphere and a slips sphere into water. What we will see here is for hydrophobic sphere, to produce a cavity, you need a velocity higher than, let's say, 4 meters per second or 5 meters per second. But for slip sphere, we can reach or produce a cavity at a relatively low velocity. That means for the same contact angle, it is easier for a slip sphere to create a cavity. So why we want to ask? And another thing we should see is to produce a cavity, the liquid sheet, this liquid should not always contact with the solid surface, right? Otherwise, it will just climb on the surface and close at the north pole of the sphere. You will not get a cavity. So to produce a cavity, later we call it a lambda. It should detach from the solid surface. So we think the lambda evolution is very important. So of course, lambda evolution is not, we are not the first one to study it. It has been extensively studied for drop impact on solid surface, this configuration. This 2012 paper, Professor Deegan's group, they studied this problem very well. So let's see, you have a droplet, it hits a solid, right? Because we think at this velocity, solid is not compressible. So the liquid from the droplet cut from this area, it has to go to somewhere else. So it expands in its neck region. You will get some liquid grow in this way and in this way, right? So later, if this liquid is come out from the neck region, we call it a lamina, okay? So from volume conservation, you can very easily to get the growth or the change with time of this RM or the neck radius. You will get it is proportional to square 2t, t is time. From the invested potential flow theory, you will get a more precise expression, which is square 3t. Okay. In this 2014 paper, Professor Galilo's group, they give a very detailed description of the lambda evolution at different stages. So we can divide it into 4 stages. First, we call it earlier spreading. Early spreading is when this droplet hits the solid surface, its neck grow, right? Before this things come out, you will just see the neck is growing. So it's called early spread. There's no lamina. But at a certain time, you will have some liquid come out from the neck region. That means the lamina radius is larger than the neck radius. We call it generation of a lamina. So the time the lamina is produced is very important. They denote it as TE, which is the ejection time. And it is calculated by this equation. Okay, that we'll use this equation. It's very important. The third part is if we want to produce a cavity, this laminar shouldn't always go along with the surface, otherwise there will no air entrapment and no cavity. So this laminar have to be lifted up or detached from the solid surface. So what is the mechanism for it? In this paper, 2014 paper, they use two force. They contribute these two forces for the lift force. One is the lubrication force, and one is the suction force, because it's like the basic Bernoulli equation. You have air, right? It just go this way and go this way. So here, the air velocity is likely higher than here. So you have a high velocity here, you have a low pressure here, you have high pressure here. So this pressure difference is the suction force. It will also help to lift up this laminar. Okay, so if the laminar lift up, of course, it is not related to cavity formation, but always we also wonder whether you have splash, right? You have a laminar, we'll always ask whether you have secondary droplets produced from this laminar or this liquid sheet. So the criteria for splash is the velocity of this ejecta or the laminar, I mean the tip, the velocity should be larger than the telequinetic velocity. That means the velocity can no longer hold the velocity, the liquid back. So splash will happen if you have this criteria. For droplet impact on a smooth solid surface, usually we have a splash parameter K, which is usually like a Webb number multiplied by square of Reynolds number. It should be larger than, or it is equals to 10,900. If you have the real splash parameter larger than this, you will have splash, okay? So now we just mentioned, we are talking about drop impact, right? So why we use water entry problems? Of course, it is because of application, but now I will show they are the same. Because we used, we did two series of experiments. First, we do water entry problems. We use hydrophobic sphere and the slip sphere with the same contact angle. We also do drop impact on a hydrophobic plane, I mean solid surface, and a slip plane. That means a solid plane covered with a slip oil. We can see slip spheres is always easier for this laminar to detach from it. And for drop impact, it's the same. This is a slip surface. This is a hydrophobic surface. So can we unify these two phenomena together? So if we imagine another configuration, a drop impact on a sphere, so you have two radius, right? You have a radius of the solid sphere, you have a radius of the droplet. We can induce a curvature ratio, which is the radius of the solid sphere over the radius of the droplets. Then you can imagine if for water entry, that means the radius of the liquid surface is infinite. So you will get alpha equals to 0, right? And for drop impact on a solid plane, the radius of the plane surface or the solid surface is infinite. So you will get alpha equals to or approach to infinity. Okay, so now the problem is whether we can use this alpha to unify these two phenomena together. What we do is we consider this configuration, right? The drop impact on a solid surface. Then from volume conservation, we can get the change with time of this arc length, which is the radius of the wetted area. And then we do a lot of experiments. We can change the drop size. We can change the sphere size, right? We can change the alpha. So we did an experiment. We draw data together. We see if we don't use the alpha, we don't take into account of this curvature ratio, then the data cannot collapse or collapse, right? Then if we put this alpha inside, all the data, I mean, collapse pretty well together. So that means essentially they have the same principle, or I would like to see they are the same problem for the early stage for the laminar evolution. And beware of that. This data is not only for drop impact on a dry solid surface. Also, we use slip oil cover the sphere, so we do drop on a impact on a slip sphere. We also do a drop impact on the plane surface with or without oil. So actually, there are many sets of experiment, and they show the same changes at the early stage. So I would like to see by induce a very simple configuration parameter, which is a curvature ratio, we can unify the earlier lambda evaluation for these two parameters together, we think they are the same. Okay, so for the cavity to produce, the lambda have to be detached from the solid surface. But unfortunately, in 2014 paper, they put this equation, but there's no analytical solution, or there's no exact ways you can calculate the lift force. So we later we refer to this paper, 2005 paper. They propose this idea is that imagine you have a drop liquid, right? It is spread on a, now it is on a slip surface, but it's not matter. Let's see if this guy want to raise up, right? That is because this yellow, I mean, the lubricant film is stop it moving or block it moving, right? Especially if this guy is very viscous, then this liquid is not easy to push this liquid away, but it want to expand, then it have to come up or detach from the surface, right? It's very easy to understand. So I think this idea is very reasonable. So the X value is viscosity ratio, which is viscosity. I mean, here is also dynamic viscosity as the mu. So symbol is different, but they are represent the same viscosity. So the ratio is gas viscosity, because before they consider is like drop impact on a solid surface in the air environment, right? In the gas environment. So the lubricant film is gas. So the viscosity is gas viscosity. So the ratio, I mean, the bottom is the viscosity of the liquid. So if you change it, then the capillary number or the critical capillary number to make this lamina to lift up is reduced if you increase this one. It can be understood like this. If the gas is more viscous, it is more difficult to push this gas away. So this lambda will be easier to lift up. So you need a little velocity of the droplet. The lambda will be lifted up. So it's very reasonable. So but the difference is here, when we use the slip surface, there is only a thin layer of oil, right? Before, if the environment is air, the whole continuous phase is air. But now you have air and you have a thin layer of lubricant film. So will this trend keeps correct? I mean, for this configuration, we'll show it later. But here we already changed. I think we have already changed. We changed the viscosity ratio between gas and liquid to a liquid and liquid, because this guy viscosity is much higher than gas viscosity, right? So we assume that we can bring down this capillary number a lot, bring down. That means we will make cavity much more easier to happen. Of course, we already see the result, but now we want to calculate these things and verify it with experimental data. So the criteria for lambda detachment is this guy. Is your capillary number should be larger than the critical capillary number. This capillary number later we get from our colleagues' paper, Professor Gopal's group. He gave a very, it seems complicated, but every the meaning of every atom is very, very clear. So we can calculate this guy. But to calculate our real capillary number for the lambda lift up, we need this velocity. If we look at the arc growth with time, if we do the derivative, we will see its velocity is decreasing with time, right? Because you do this for differentiate for time, you will get a negative for power of this t. That means the velocity is decreasing. So if this guy can be lifted up, it must lift up at as early as possible, right? But we know at the earliest time for the lambda is Te. That is the time it is first produced, right? So in this equation, that means we just need to differentiate this guy to get the velocity and put Te here. T we can calculate from the 2014 paper. So we can calculate our real capillary number and the critical capillary number, then we compare them. So if we use this guy as a lubricant film, we don't change the lubricant film, we just change the, what we call the curvature ratio, right? We will see our calculated number is agrees pretty well with our analytical value. I mean, this one. So it agrees pretty well. Furthermore, we also investigate if we change the viscosity ratio of the lubricant film and the droplet, what will happen? Because now we can do it, right? Because here, I mean, we can change all these numbers. So we use silicon oils of different viscosities as a looping film and do the experiment. Our data shows here R is the viscosity ratio. We see our experiment value and the theoretical value agrees very well. Okay, also for the cavity formation, we see a very clear tendency, which is predicted well by the analytical solution. Okay, so now let's go back to the first question. If we use this slippery liquid-liquid interface, whether it helps to produce a cavity, the answer is yes. So this figure, the X value is the thickness or the non-diminished thickness of the looping film. Of course, if it is 0, that means you use the hydrophobic dry solid surface to the water entry problem, right? So we see the threshold velocity or the minimum velocity to produce the cavity is about 4.5 meters per second. But if we use the same contact angle but a slip sphere, you can bring down this velocity to like less than 2 meters per second. That means at the same contact angle, a slippery liquid-liquid interface does help for the drag reduction, or to produce a cavity first, right? For the drag reduction, we have to calculate it. We calculate this drag coefficient with Reynolds number. So this yellow data is for the slip sphere, and this blue one is for the hydrophobic surface with the same contact angle. So we see for the slip sphere, for a larger range of Reynolds number, you can realize drag reduction. Okay, that is the key findings of this part. Later, we also observe what it looks like the triple line for these two different configuration. Here is the hydrophobic sphere, and this one the sphere, slip sphere. We see actually if they can produce a cavity, there is essentially no difference at the configuration of the cavity and also the triple line. It looks the same. That means the key changing is during the laminar evaluation at the very early stage. So that is a key. Okay, so we know that because just now we mentioned the fourth stage for the laminar is whether it can splash, right? So in 2005, Professor Xu Lei, he found very interesting that if you reduce the pressure of the environmental gas, it will make a splash difficult to happen. So it's a very elegant work, but we always ask when this film splash, why it is not symmetric along each circle, right? Of course, it cannot become always asymmetric because this film, sooner or later, it has to break because it will become thinner and thinner, right, when it expands. So that means it will always break, but what is the reason cause it to become destabilized, right, or destabilize it? So to consider this problem, we do the configuration again for drop impact on a liquid pool, not on solid surface. Later, I will explain why we use this configuration. So consider you have a droplet, you have a shallow liquid pool. After they interact, right? What we call here is the ejecta sheet. That means it's a very smooth liquid sheet comes out and grown in time. You can have splash if your impact velocity is high enough. So basically, we see for drop impact configuration, you have two very important mass transport mechanism. One is splashing, one is air entrapment under the droplet. That means the drop will also capture a certain amount of gas or air under it. So we think this is two very important mechanisms. So there are review papers and some very basic questions related for this problem. But now let's go back. We want to ask where is the reason for the instability comes, right? So here is the setup. We use a ultra high-speed camera to study this problem, and we look upwards, right? Here is the drop impact on this pool. We look from down. So we just look at this tiny region, and we use a very high magnification. So, okay, here I will show a video taken at 5 million frames per second. My colleague Mahijan Tova, he probably the first guy to observe this radial line during drop impact on liquid surface. What radial line I'm talking about is this kind of lines at this region. Okay, so before why we couldn't see it, because they are the same liquid, right? Even you have this interface fluctuating, there's no difference between these two liquids. The light can just pass through directly, right? But now what we do is actually we add some salt into the liquid pool. So the refractive index of the droplet and the liquid pool is different. So when the surface is fluctuating, when light transfer this interface, it will get disturbed. So you will see this surface structures. And more importantly, we realize it within 60 microseconds, the really instability induces this radial length. And later, more importantly, it causes the vortex shading lose its symmetry in the circle direction. And but why? How it can relate to splash? Later, if we observe very carefully, we see when the lamina breaks up or the ejector sheet breaks up, we always see it only splash from the region where it don't have this vortex shading. You can see here we have splash, here is no vortex shading. Here we have vortex shading, there is no splash. So we first observed this kind of link. So we think because vortex shading and the splash is alternate along the circle direction. So the very early instability from the sharp corner of the ejector sheet between the other two interface, liquid air interface, from that region, there is an instability comes up, and this instability causes this radial line, which breaks the symmetry of the vortex shading, then later breaks the splash symmetry. Okay. Then another very interesting question is if we actively break the symmetry, what we will get? So we do this experiment. We use a compound droplets. That means we have a external droplet, but we put some inner droplet inside it. In this configuration, we use water outside and heavier or denser perplexing liquid in inner. So this droplet is heavier than the water droplet. It will accomplish at the bottom of the big droplet. Then again, we use high-speed imaging to see it. So if the droplet is hanging at the nozzle, because there is a density difference, we can imagine it will have some bump come up because of the density difference, right? But then if the droplet is released from nozzle, it is a free fall. This guy should disappear, but in our experiment, we still see this guy. Sorry, we still see this guy. That means time is not enough for this guy to recover to become smooth. So this might affect the later dynamics. We just we think it is. So there are some videos. Okay, this guy has how many? Like 6 inner droplets inside. But more importantly, we see only jet at the orientation of the inner droplets. So here, this orientation, you don't have inner droplets, there is no jet. Okay, if we zoom in, we see this guy. And it seems the jet has some relationship with this bump, but we are not very clear at this point. Okay. So, but we propose it is a new mechanism for the splash of the jet to happen. We call it inertial focusing. Why we see it like that? Because later we change the viscosity of the external liquid, like from here is like 110 something to over 100. For this large range of viscosity ranges, we see the velocity of the jet and the size of the jet almost keep constant. So it apparently is not because the focusing of this external liquid is not from that mechanism, right? Otherwise, it must be related to the viscosity of the external liquid. So we think that is some hint or proofs for this inertial focusing mechanism. Okay, so this picture shows if we have some denser inner droplet inside, it will make splash easier to happen. That means it also has influence on the splash threshold. So this droplet and this droplet have the same velocity, but here n is 0, means it has no inner droplets. We don't see the splash or the jet, right? And this guy, it has 4 droplets. So one is here, and another one should be in this direction. So you have 4, and we change the orientation of the camera so we can see these 2 sides jet very well. And this is just for show if you have many droplets inside, what it will looks like, right? Okay. So that is my first part. It means the Lamella evolution is very important for cavity formation during water entry problems, but also for drop impact experiment, the earlier Lamella evolution, I think it is the same problem as the water entry problem. So they are the same for these two configurations. The second part is the drop manipulation. We discovered what we call the inverse square force between two evaporating session droplets. Okay, what is that? Because we have said, right, we focus on the mass transporter in this talk. So Churchill side, victory is the beautiful bright colored flower. Transporter is the stem without which it could never have blossomed. That means transporter is very important mass transporter, right? I mean, for a drop system, it's the same. So how can you transport a droplet? I mean, you can use gravity like the rain, right? But recent years, there are also many other active methods have been proposed, like you can use shear, inertial electric field, light, and the gradient of different things like structure, topography, or temperature, or waterability, or humidity. This gradient also can cause drop to move. And in 2015, there is a very nice paper by Sarah and colleagues. So they realize if you have two session droplets putting on a solid surface, they use binary droplets, means it is a mixture, is this PG and water solution. PG evaporates slower than water. So if you put two droplets on solid surface, because this region overlaps, right? So the water will evaporate slower at this region and faster at this region. We know that when you evaporate faster, you will get a lower temperature, right? Which will affect your surface tension. Means here, evaporation is low. Okay, so your temperature is, let me see. Your evaporation is slow, so temperature is here, so your surface tension should be low, right? Okay, so I mean, from experiment we see they can both attractive or repulsive. So it doesn't matter. I mean, for this configuration. But that means these two droplets will have force exert A on B and B on A, right? That is because of uneven evaporation between this region and this side. Okay, but in its paper and the following studies, there is no analytic solution or concise expression for the driving force. It's always you need to integrate like a complex form to get estimation of the force. But if we consider the problem, we know that the humidity or the vapor concentration, it is satisfy Laplace equation, right? It's a very simple equation. So we believe there should be some simple form of the force we should be able to find. So our objective is to find a concise form of the force. Okay. So first we have to do very high precision experiment first. So this is my PhD student. Now he's a doctor, Zhang Zhu. So we use the same liquid, but we do the experiment in an environment chamber, which is the temperature and the humidity is controlled very well. Okay, so let's see this configuration, I mean the setup. And this is a typical video to show the attraction of these two drops. So if we compare our data with the previous data, we see the spread in our data is much smaller than the 2015 paper, right? So this is first what we need to get high precision data, then we do the analysis. Here, what we do is a very, you may think is a very strange data transformation, but it is very useful. That means first, what we get is here, tau minus t. This tau means the time when the two droplets meet. So when tau equals to t, I mean t equals to tau, that means you get the 0 for this guy. So the two droplets meet, right? So the L, the distance between here, not the center to center, is from here to here is 0. Okay, this is original data or raw data. So what we do is we keep this the same, but we change the y value to this form. You may ask, this looks very strange, but it's very useful. So this form is very easy to get from our experiment data. What we have is we have L, we have the R, that means the radius of this film, right? So we can do this. But then, very strange, we change all the curved lines into straight lines, and these straight lines all pass the origin point. That means it passes the 0 point. Okay, then if we write this lines, right, it's a linear relationship between this guy and the right term. There's of course there's a coefficient or prefactor k. If we take a derivative for this form, we'll get this guy, right? Derivative for t is very easy for this one. And we have the kinematic relationship. That means this drop, if they are the same, this guy will have the same force on this as compared to the force from this guy on this, right? So they will move at the same velocity. So you have the velocity, that means the definition of L to T is the 2 times of the velocity. U is the velocity of this drop, also the velocity of this drop. So you have this kinematic relationship. You put this guy to you to here, you have this relationship. This is very important because we know usually for such a very thin liquid film moving on a solid surface, it usually is a Stokes flow. That means we can use this guy to predict the resistance. That means it is highly possible proportionate to the velocity. And we see the left term, it is proportional to velocity. So we can consider this as a resistance force. And is equal to this guy, right? So, and when it moves very slowly or for this configuration Stokes flows, we can imagine the driving force probably is also equal to the resistance force, means it is a static equilibrium system. So we can consider this as a driving force. And you can see L is this guy plus 2R, that means this distance, that is the distance between the 2 centers of the 2 droplets. So if this guy is a driving force, it is an inverse proportional to the square of the distance. That's what we call the inverse square force. Okay, the inverse square force in the nature, what we have is a Coulomb force and the gravitational force, right? So it's very straightforward to compare with the historical track. Like when Isaac Newton to derive the law of the universal gravitation from, of course, from Kepler's 3 laws, right? From this three law, we call it kinematic relationship. That is observed, right? You observe the planetary, then you get these 3 laws. These 3 laws, the Newton's law is Newton derived by himself. So you plus kinematic relationship plus the force relationship, Newton got derived the law of the universal gravitation, right? So just now the previous slide, we use this L3 relationship. L3 means the distance cube, right? This is also a kinematic relationship. And we use this scalar law of the resistance because we think the resistance is proportional to the velocity, right? We call this force relationship. Then we get an inverse square force. It's very similar, but unfortunately, these laws are very famous, right? Everyone will accept it. And this relationship is just an empirical new formula, right? If I persuade some guy to believe it, probably they will not. So I have to prove it. I have to derive the expression form of the force. So that is what we do now. Consider this configuration. You have a thin film on a solid surface, right? So we have this equation, I mean the relative humidity equation. We can solve it with free form. I mean, actually, we use free form to solve it. So what we get a solution like this guy. So it works pretty well with the theoretical solution and what is so called this guy, the blue line, the theoretical curve, and this guy. Let's see. Okay, this answer take the result. So we use this guy later as distribution of the relative humidity in the space because it really works pretty well. Okay, so next, now we know how the phi is distributed in the space. Next is how phi affecting the surfactation, right? Surfactation, I mean, along the droplet, like along this circle, the surfactation is different. Like the length of this arrows represent the strength of the surfactation at this region and at this region. Then if we know this surfactation, we do an integration, we know the force, right? So we take the idea from the 2015 paper. So they think because of evaporation, what change is here? This guy changes. So the gamma, this guy, they think for the binder droplets, I mean the water PG solution, there is a precursor film. So this guy, because the evaporation, it will change. And this guy, the main part of the film, the surface tension of the liquid is not changing. It's okay. I mean, you can also assume another way. I think it doesn't matter. So this guy changing, this guy is not changing. So your contact angle is changing, right? So because you have to fulfill the Laplace equation. So we do experiment, we change the humidity, and I think we change the evaporation rate, so we can change this guy. We should measure different contact angles. So that is our experiment data, I mean, these dots. So you can see in literature, there are 2015 paper, they think the the contact angle and the phi humidity, they should follow this guy. And there's another 2017 paper, they think it should be this guy. But in our data, we think it fulfill better in this way. But I'll show later, no matter which way you use, it doesn't matter, it's not affect the inverse square form of the force. So that is a very key point we want to see. The relationship between contact angle and the local vapor concentration is inclusive, but its specific relationship doesn't affect the inverse square form. Okay, so we derive the driving force. So I will not go to the details. So basically you do an integration to the phi, right? Sorry, I have to go back. Phi is this angle. You do an integration, you get the force. So of course there is some residue. So we realize we get this force is a very clear form because every item we know what does that mean, what it means. And we found that when the distance between the two droplets, the H, the L, when it is larger than L, the residue is smaller than 5%. So we think this expression is pretty precise. Now we know the driving force. If we want to compare our theoretical value with experimental, we also need to know the resistance. The resistance, usually people think if this film moves during it moving, if the contact angle keeps the constant, the resistance goes this scaling law. If it changes during motion, then you have to use the Cox theory. The resistance will be this one, I mean to the 2/3 power of the velocity. To verify which one is better, because we want to see the expression is very rigid, right? We have to remove any other influences on the derivation. So even it is like 1 and 2/3, we have to choose or decide which one is better. So we do this experiment. We let the thin liquid film sliding down along a thin wafer, which is TTO'd at 15 degrees, because we know the gravitational force very well, right? So it will accelerate at the beginning, but it will reach a terminal velocity. Then we can measure this velocity. Then we know the gravitational force. We know the resistance force, right? So this is the data. Both, if you use either way, it works pretty well. But we think this red dots means you use this guy, it works even better, right? As we can see from this data. So we use this one as the resistance force. Now we know the driving force, we know the resistance force. We can compare our theoretical value. That means theoretical key, because you know this is the resistance force, you know, driving force, you know, the kinematic relationship. You combine this together, you get this prefactor key. This is from the analysis, we call it a theoretical value. Then we have the raw experimental data, right? You can measure this prefactor directly from this figure. We get the experimental value K. Then we draw these two K together. We can realize that we calculated for different models. That means if you use different relationship between contact angle and phi, but we realize it doesn't really matter. All of the three types, I mean, the model works pretty well, but we think this guy, the quadratic relationships, seems works even better, right? But we insist to mention that the specific relationship of the contact angle and the phi is not important. The R square relationship. Sorry, the L cube relationship is more important. This we always insist is our point. Okay, so now we know the force. We want to know how well this force can be applied to different systems. Also, what we call is a universal applicability. Then we try the different systems. We change the size ratio of the two droplets. We see it works pretty well. When we see it pretty well, that means it changes to a straight lines passing the origin points. Okay, then we know the force, the form should be inverse square force. We also change the concentration of the PG solution, and it also works well. We change to pure liquid system, means before we use binary liquid droplets, but now we use pure liquid. We see it works well. This data is not our data, it's from 2019 paper. We get their data, then we redraw it. We realize it works very well. This is from Professor Chuan's paper, 2017 paper, is a thermocoupled system. That means you have two droplets floating on a liquid surface, but we realize it also works for this system, thermocoupled system. That means seems this inverse square force apply very well for different systems. Later, we also compare it with universal gravitation. So if you have two celestial bodies, if you have two session droplets, the plot is like this. We also propose a potential because we know for gravity, it has a potential. You do the derivative, you get the force, right? So for our system, we also propose a homogeneity potential. Then you do the derivative, you also get the force, and we verify that it works. The last, we show that it also satisfies the superposition principle, but we should mention that for gravity, there is no limit that for that equation, because in the real space, there is no limit how much mass it can sustain, right? But in our system, I mean, for humidity, it cannot exceed 1, right? The relative humidity, it cannot exceed 1. So that is the only restrictions when we compare these two. But when we adjust it to the upper limit of 1, it works. I mean, it fulfills the superposition principle. Now, I mean, this work is not published yet, but we put it on the archive. If you are interested, you can get more details for this. So now go to my conclusions. So I think for the drop impact and the water entry problems, we see that we realize that the Lamella evolution is the same for these two problems, and it is very important for cavity formation. And we observe that for the same contact angle, a slippery liquid-liquid phase can reduce the drag better as compared to its counterpart. I mean, the hydrophobic surface with the same contact angle. And for the evaporating drop systems, we discovered a new inverse square law force in that system. Okay, now I have to acknowledge my PhD students. I mean, the work I talked today is basically from these 3 students, Zhu Jiang, Tao Wu, and Rui Chen, and also my previous colleagues, Professor Sorensen, and Ding Hang, Ma Zhang, Wang Zuankai, and Guo Peng, and also the funds I got from the university and the National Science Foundation of China. And okay, that's my talk. Thank you for your attention.
Thanks, Chang. Thanks, Professor Ni's very, very nice talk and a very solid work.
Thank you.
So any question from our audience, you can unmute yourself and ask Professor Ni directly. So any question from our audience?
Yes, hello. It's really also, I mean, I found it a very nice talk.
Thank you.
As well. I had a question on, in the first part of your presentation, you have shown the drag coefficient as a function of the Reynolds number.
Yes.
There was a kind of crisis right there.
Yes.
Sorry if you already mentioned it, but I didn't.
You mean this one?
Yeah, yeah.
Yes.
So what is this jump?
Jump. Okay.
Yeah.
The jump means if you use, let's say the red dots, right? Means
yeah,
it's a slip sphere. You throw it into water, But if Reynolds number is smaller, means you release it with a lower height. That means it has a smaller velocity. So at this stage, it cannot produce a cavity because we can see from here, it needed some velocity to produce a cavity. So it cannot produce a cavity, the drag is large. But if it exceeds this velocity, yeah, you reach this cavity.
It's related to the cavity. Yeah, sorry, of course you mentioned it in the beginning, but I was maybe not.
No, sorry, I didn't mention it. So your question is very, very good, yeah.
And you have tried to play with the surfactants or, I mean, things on the interface?
You mean for this program?
Yeah.
No, we didn't try surfactant. So surfactant is bring another influence, is like more like a surface tension, right? So so if we look at Professor, I mean the Doo's paper, so you can estimate how surfactant will change, because I think here you have this guy, right? This is surface tension. So if you increase surface tension, or if you use surfactant, your surfactant become lower, that means it will bring the velocity down. That means if you have a surfactant, it might easier to produce a cavity. So we can refer to this graph here.
Okay.
Yes, but we didn't try that. Yes.
Okay, and maybe a last question in the second part. Can you please say again how you distinguish between the, I mean, from conceptually, how you have distinguished between the driving force and the drag? So in your computations.
Oh, okay. Okay. So we do experiment, right? So
yeah,
we do experiment because we know the angle very well. So and we release this droplet, it become a film and sliding down. So it will be accelerated at the beginning, but it will reach terminal velocity. So when it reaches terminal velocity, we know the gravitational force and the resistance force is the same, and we know the gravitational force. So we know the resistance force. Then we do different drop volumes here. Basically, it's change the drop volume. We get many data points. Then we see these two forces which predicted better.
And okay, so you were subtracting the drag force from the other one with evaporating droplets, and then by subtraction you deduced what's the driving force, right?
When we do the analytical or the theory, so we do them separately. Of course, later we always use the equation is like the resistance is equals to the driving force to get the prefactor key. Because in reality, when these two films approaching each other, we think it's like a quasi-static equilibrium system. We think they are the same, yes, because velocity is very slow and yes.
Okay, that's interesting. No, yeah, okay. Yeah, that's interesting. Actually, it's really like simulations, because in simulations, sometimes you measure the total force, but then you cannot distinguish the contributions. And of course, you need some assumptions. So here, your assumption is the quasi-steady state.
Yes, yes.
Thank you very much.
Thank you for your questions.
Yeah, thanks for your very nice talk, Professor Lee. I have a question.
Yes.
So for your experiment, you use a very ultra far high-speed camera, but for the coalescence of droplet, so can you observe exactly the contact of the two droplet, and how about the error of your measurements?
Okay, Professor, it's a very challenging question. I mean, even we use the actual high-speed imaging, if you want to measure the, I guess your question is to ask how measure the neck radius during the coalescence of two drops, right?
Yeah.
So even use actual high-speed image, it is not fast enough. I would like to see even we use 5 million frames per second, it is still not fast enough. Depends what you want to see. So if we use this kind of high-speed camera, you will see the radius is growing versus time, I mean, probably you will get a law like 1/2. That means half. You will think it is like a not inertial dimension. It's like a viscosity and viscosity both important. But actually, I think Professor Nico's group, they use electricity measurement. Means you have two droplets like this. Then they use two wires connect one guy here, one guy here. Before the coalescence, there's no connection, so you get the voltage or the resistance is infinite. I mean the electric resistance is infinite. Then if these two match together, you have a bridge. So you can think it is like a disk. We know the resistance for a disk, so they use this method because the electric method you can measure like nanoseconds, picoseconds or femtoseconds, which is much powerful than high-speed imaging. So they can observe a region which is this arc or the radius grow with time as 1 power. I mean the power exponent is 1. This is very difficult or very challenging from high-speed imaging to observe this region. I mean that is within like 100 nanoseconds or something.
Okay, thank you very much. Very nice.
Thank you for your question. Thank you.
So any other question from our audience? So Dr. Lee, I have a question about the inverse square law for the attraction force between the droplet. So
Yes.
you mentioned that you use others, also use others data, for example, the droplet, the suspension on the liquid-liquid interface. But in your experiment, you are doing two droplets, and actually the slip on the solid surface. I'm not sure, because in the formula there is no consideration. For example, you have the if you introduce this solid surface, you will have, for example, the roughness or the contact angle problem, and also you may introduce the liquid film generate between on the solid surface. I'm wondering how different from the suspension droplet case and the solid the two droplets sitting on the solid surface. How many the difference in your analysis? Because there's I think there's no any roughness, steepness kind of thing on your formula, but actually the formula is very powerful, can predict both this case.
Yes, you ask a very good question. So I mean, when we do the analysis, actually this system, I mean the floating on the liquid surface, is different from our experiment. So the reason cause these two droplets to move is called the thermal stress, is not the surface tension gradient. So if we take at the problem as this view, you have two droplets on a solid surface or on a liquid surface. Whenever you have some effect from one guy, so because we know it's like you draw lines through the center to outer, so the density of these guys, or because the surface area is expanding. So for this guy to sense the change of here is like how much you blocked, is like an area you blocked at the projection of this thing. So basically that is the idea for all the inverse square force. So I think that is principally the same, but these two questions, they are different questions. But if we take into account the thermal stress, you will see the thermal stress is also like a inverse proportional to the distance. Then the change of this guy is kind of similar of the change of the relative humidity in the space. So I guess in this sense, they are similar. And when we do you can see when we do the same change here, we see they have the same L square L cube, sorry, I will say L square, L cube formation. So I didn't put the unless here. So if you don't mind, I can show it here. So when you see this guy, I mean the two droplets on the liquid surface. So actually, this guy is what you call the thermally affected area, which is also proportional to the square of the distance. So in this sense, they give you the same form of the force. But you are 100% right, correct. There are different problems. But like the split length, this sense, the slip length, it probably affects the resistance. When the drop is on the solid surface. But the overall, the outcome seems what we get is this simple or concise form.
Okay.
Yes.
Thank you. It's a very interesting formula, and this.
Thank you. We hope. Yes, we hope the community or the colleagues can have this in mind. So whenever you do this kind of experiments, like either evaporation or the thermocapillary system, you can try to draw your experiment data in this way, right? If in this way you do the differentiation form, usually, that means whenever you have this form, that means probably there is some inverse square force here. So I think that is more important to our community.
Okay, thank you, Archon. So if we have additional question, and you actually can contact Professor Lee directly, and his information actually is on our website, and also here, if you want to ask a further question, you can contact Professor Lee directly. Okay, then we will end here today. Thank you very much for your attending this seminar, and thanks very much